Think about the last piece of high-end tech you bought. It's probably a solid slab of brushed aluminum or, a perfectly sealed, glowing pane of glass.
Oh, definitely. Completely seamless.
Right. Modern consumer technology is deliberately designed as this black box. You aren't supposed to know how the magic happens, right? You're just supposed to interact with that polished surface.
You just touch the glass, that works.
Exactly. But then you look at today's subject, and it is a total visual rebellion against that entire philosophy. You're staring at a bare green circuit board.
Just completely naked hardware.
Yeah, you can see the silver soldering, the exposed GPIO pins, the microchips just sitting right there in the open. It looks like, I don't know, a prototype that escaped the lab before the design team could even build a case for it.
Right, they forgot the plastic shell.
And yet this raw, unfinished-looking little rectangle has fundamentally rewired modern computing over the last decade.
It really forces a complete reset of our expectations. I mean, we're so conditioned to equate computing power with massive server racks or heavy gaming rigs.
Oh, for sure.
So seeing a device practically the size of a credit card, it feels almost entirely out of place in a serious technical discussion.
And breaking down that exact contradiction is our mission for you today. We are doing a deep dive into the Raspberry Pi ecosystem, and we're pulling from a really brilliant stack of sources to do it.
Some great reading material today.
Yeah, software engineer Aaron Rose just published a fantastic piece today, June 13th, 2026, over on tech-reader.blog. It's titled Raspberry Pi in 3 Minutes.
A really concise overview.
It is. And we're also pulling from a handful of his highly technical deep dives on the same blog that break down the actual architecture and deployment of these boards. Our goal for you is to strip away the assumptions.
Right, get past the surface level.
Exactly. We're looking at how this device evolved from like a classroom experiment into an enterprise-grade tool, the extreme lengths developers go to optimize its software, and how it's currently being pushed to its absolute physical limits.
It's quite the journey.
Okay, let's unpack this. When we look at the raw architecture of a Raspberry Pi, we are dealing with a fully realized system on a chip, right?
Precisely. It is a single-board computer. You have the CPU, the GPU, the RAM, and the network controllers, all just engineered onto one incredibly tight footprint.
So no slots, no plugging things into a motherboard.
Right, you aren't dealing with a traditional motherboard where you slot in separate components. The integration is absolute. If you take that board, supply it with power, flash an operating system onto an SD card, and plug in your peripheral.
A keyboard, a mouse, whatever.
Exactly. It handles standard desktop workloads without breaking a sweat. It compiles code, runs Docker containers, manages databases.
But the architecture itself isn't what makes it fascinating. I mean, we've had compact computing for a long time.
Sure, many PCs have been around.
Right. What strikes me is the psychology of the physical design. If the original goal of the Raspberry Pi Foundation was purely educational, like to get kids coding, why not just wrap it in a cheap, rugged plastic case?
Like a tough tablet or something.
Yeah. Why leave the engine exposed?
Well, because the exposed engine is the core of the pedagogy. When you hand someone a sealed, finished laptop, even a cheap one, it communicates a very specific relationship.
Which is what?
It says, I am an appliance, consume my services, but do not alter me.
Wow. Yeah. Look, but don't touch.
Exactly. But the moment you hand someone a naked printed circuit board, you completely shatter that dynamic. You're communicating that the hardware is malleable.
That makes a lot of sense. It's practically daring you to wire something into those GPIO pins.
Go ahead, plug a sensor in.
Right. It removes the preciousness of the technology. Like if you accidentally fry a $30 board by crossing a wire while building a temperature sensor, it's an annoyance, you know? It's not a financial tragedy.
It's the cost of a decent lunch.
Yeah, and it shifts the user from a state of passive consumption to active hardware engineering.
And that low-stakes environment is exactly what catalyzed its massive adoption. By removing the financial risk of failure, you accelerate the iteration cycle.
You just try things faster.
Yes. Hobbyists and professional engineers realized very quickly that the same lack of friction that makes it great for a middle school classroom makes it an incredibly powerful sandbox for rapid prototyping.
I want to push back on that transition, though. Aaron Rose's blog post makes a very bold claim that we need to stop calling the Raspberry Pi a toy because major organizations are deploying them in real-world, highly demanding production environments.
There's a big claim.
I mean, I understand using it to prototype a deployment in a lab, but actually relying on a piece of educational hardware to run enterprise infrastructure, that sounds like a catastrophic point of failure waiting to happen.
It sounds terrifying if you think about it traditionally.
Right, you don't run a critical corporate network on a $30 board.
It sounds like a liability if you evaluate it through the lens of traditional monolithic server architecture. But what's fascinating here is that the Raspberry Pi actually thrives in production because it forces you to design better, more resilient systems.
Wait, how does using weaker hardware force a better design?
Let's look at the mechanism of how companies actually use them. They don't typically run their entire database on a single Pi. They build clusters.
So instead of buying one massive $10,000 server, they network, what, 50 Raspberry Pis together?
Exactly. And the open nature of the Pi is what makes that possible. Because it runs standard Linux distributions, the software stack is enterprise grade, even if the hardware is a commodity.
Okay, so the brain is smart even if the muscles are small.
Right. And if you design your system using microservices, and one of your nodes, one of those 50 Raspberry Pis, experiences a hardware failure.
Because it's a $30 board and it just dies.
Yeah, it happens.
Yeah.
Your load balancer simply redirects traffic to the other 49. The cluster self-heals. You literally just walk into the server room, yank out the dead $30 board, slot a new one in, and the system provisions it automatically.
That completely flips the risk model. You aren't trying to build a single indestructible machine. You're building a fragile, disposable fleet that is collectively indestructible.
The swarm survives, even if one bee drops.
Yes, the fact that the hardware is so cheap and standardized is exactly what makes that redundancy economically viable.
And beyond clustering, Aaron Rose points out that the technology landscape shifts incredibly fast.
Yeah.
We are constantly seeing new deployment frameworks, new IoT protocols, containerization strategies, you name it.
It's impossible to keep up.
It is. And the Pi endures because it is the ultimate blank slate. It isn't bogged down by proprietary enterprise firmware. It gives systems administrators a standardized, low-cost target to test new infrastructure configurations before rolling them out to the heavy iron.
Which naturally leads to a major technical bottleneck. If you're a systems administrator or even just a power user building a complex smart home architecture, and you're treating this blank slate like a serious production machine,
We're going to hit a wall.
you quickly run into the reality of your physical hardware constraints. You don't have terabytes of RAM, you don't have massive CPU caches. Every single background process on your operating system is eating into your processing budget.
You hit the software wall. When the hardware is constrained, the operating system becomes the primary battleground for performance optimization.
And one of the deep dive articles from the source material tackles this exact battleground head on. It's an analysis of the minimal OS showdown for headless setups.
A great comparison.
Yeah, the piece specifically looks at running a network-attached media server on an older Raspberry Pi 3B Plus.
Which is pretty legacy at this point.
Exactly. Because the 3B Plus is working with older silicon and a very limited memory pool, the author has to choose between two highly stripped-down operating systems, Raspberry Pi OS Lite and Diet Pi.
And for a deployment like a media server, where you're transcoding video files or handling heavy database queries from multiple users on the network.
Heavy lifting stuff.
Yeah, the efficiency of that OS choice dictates whether your video buffers seamlessly or constantly stutters.
So what does this all mean for the architecture? Both of these systems are headless, meaning they've already ripped out the graphical desktop environment to save RAM.
Right, no windows, no icons, just a command line.
But Diet Pi takes the minimalism to an almost obsessive level compared to Pi OS Lite. I'm trying to visualize the difference in how they actually manage the system resources.
The difference lies deep in the kernel configuration and how the OS handles background services. Raspberry Pi OS Lite is essentially a stripped-down Debian distribution.
So it's still pretty standard Linux under the hood.
Right. It removes the GUI, but it still runs a fairly standard suite of system services in the background. It assumes you might want to easily plug in a Bluetooth dongle or run standard cron jobs or use complex networking protocols.
It leaves the doors open for you.
Exactly. Diet Pi, on the other hand, aggressively prunes those services. It actively disables anything that isn't absolutely critical to keeping the system breathing.
It's the ultimate backpacker mentality. Like, if Pi OS Lite is packing a standard hiking bag where you bring a tent, a sleeping bag, maybe a portable stove.
You're prepared for a comfortable trip.
Right. But Diet Pi is the ultralight hiker who cuts the handle off their toothbrush and sleeps under a tarp just to shave a few ounces of weight.
That analogy holds up perfectly when you look at how DietPi handles disk I/O, which is a notorious bottleneck on Raspberry Pis because they run off micro SD cards.
Which are not designed for heavy read-writes.
Exactly. Constant read-write cycles not only slow down the system, but they physically degrade the flash memory on the SD card over time. DietPi mitigates this by using a system called RAM-log.
Okay, that is a brilliant workaround. Instead of constantly writing system logs directly to the physical SD card, it carves out a tiny temporary disk in the system RAM, writes the logs there, and only commits them to the physical card periodically or when the system reboots.
It drastically reduces I/O wait times. So while PiOS Lite might leave your CPU waiting a few extra milliseconds for a log file to write to the physical card, DietPi keeps the CPU fed and moving.
Those milliseconds matter.
Huge difference. When you are asking a Pi 3B Plus to transcode a high-definition video file on the fly, those saved milliseconds compound, and they are the difference between a smooth stream and a dropped frame.
But let me challenge the necessity of that. Is it really worth managing a hyper-specialized OS like DietPi for a standard home project? Or is it just like a placebo for tech enthusiasts who like looking at incredibly low RAM utilization metrics on their dashboards?
They do love their dashboards.
Right. I mean, PiOS Lite is officially supported and incredibly stable.
It depends entirely on your hardware generation and your workload. If you're running a simple DNS sinkhole to block ads on your network, PiOS Lite is more than efficient enough. The overhead won't matter.
Okay, so overkill for simple tasks.
Right. But the author's point in using the 3B Plus for a media server is intentional. When you are pushing legacy hardware to its absolute limit, the OS optimization is not a placebo.
It's survival.
Exactly. It is the fundamental mechanism that allows the project to exist at all. You are trading the out-of-the-box convenience of PiOS Lite for the raw, unbridled performance of DietPi.
That makes perfect sense. Optimizing the software is how you survive constrained hardware. But eventually, software optimization only gets you so far.
You can't code your way out of slow physics.
Exactly. At a certain point, you hit the physical limits of the silicon. Which brings us to the next evolution covered in our source material, how developers are pushing the newest hardware into the most computationally demanding field in modern tech right now.
Artificial intelligence.
Artificial intelligence.
This represents a massive paradigm shift for the Raspberry Pi ecosystem. The conversation moves away from the legacy constraints of the 3B Plus and focuses entirely on the architecture of the Raspberry Pi 5.
And the physical specs on the Pi 5 are staggering when you remember the size of the board. We're looking at a quad-core Cortex A76 processor clocked at 2.4 gigahertz.
It's a beast for its size.
It is, but the real game changer mentioned in the article is the memory architecture. You can configure it with up to 8 gigabytes of LPDDR4X RAM.
That memory specification is the critical component. It isn't just about the sheer volume of 8 gigabytes. It is about the memory bandwidth.
How fast the data moves.
Yes, the LPDDR4X standard drastically increases the speed at which the CPU can pull data out of the RAM and process it.
Why does that specific bandwidth matter so much for AI workloads compared to running, say, a media server or a database?
Because of how machine learning models actually function. An AI model is essentially a massive collection of weights and parameters, matrices of numbers that need to be multiplied together to generate an output.
Lots of heavy math.
Tons of it. To run an inference, the CPU has to constantly shuttle those massive matrices from the RAM into its processing registers, do the math, and shuttle the results back.
So it's a traffic jam.
Exactly. If your memory bandwidth is narrow, your CPU spends most of its time sitting idle, waiting for the data to arrive. The Pi 5's upgraded bandwidth keeps those Cortex A76 cores constantly fed.
But I have to ask the obvious question here. If we're talking about shuttling massive matrices of data, that is exactly what giant server farms and dedicated GPUs are built for.
They excel at it.
Right. So why on earth are developers trying to shoehorn an AI model onto a Raspberry Pi 5 on a local desk instead of just sending the data up to the cloud via an API, letting a massive server do the heavy lifting, and receiving the answer back?
If we connect this to the bigger picture, you're hitting on the core philosophy of edge computing. Sending data to the cloud is easy, but it introduces 3 massive friction points.
Latency, bandwidth, cost, and privacy.
Precisely. Latency, bandwidth, and privacy.
Let's use a real-world deployment to visualize that. Say you have a manufacturing plant, and you want to use a camera to monitor a high-speed assembly line for defective parts.
Perfect example. If you rely on the cloud, that camera has to stream high-definition video continuously over your factory's internet connection
Which eats up massive bandwidth.
and costs a fortune. Then you have to wait for the cloud server to process it and send the signal back to stop the line if it sees a defect. By the time that round trip happens, the defective part has already moved 30 feet down the line.
Oh, wow. Yeah, that latency makes the entire system useless.
But if you deploy a Raspberry Pi 5 directly at the edge, literally physically attached to the camera on the assembly line, it doesn't need to stream the video anywhere.
Because it's processing right there on the device.
Exactly. It pulls the video frames directly into that fast LPDDR4X RAM, runs the AI model locally on the Cortex cores, and triggers the physical switch to stop the line in milliseconds.
It operates entirely off-grid. It solves the latency problem. It drops your cloud computing costs to zero. And because the video feed never leaves the factory floor, your proprietary data remains completely private.
Exactly. It's a closed loop.
That is an incredibly powerful architecture. But Aaron Rose's deep dive does issue a stark reality check about running AI on the edge.
Yeah.
The Pi 5 is powerful, but it is not a magic bullet.
Far from it. The fundamental limitation of the Pi 5 is that it lacks an NPU, a neural processing unit, and it doesn't have the heavy-duty, power-hungry GPU architecture that massive AI models rely on for parallel processing.
It's not an NVIDIA data center card.
No, you are relying entirely on the CPU cores to do the math.
So how do developers actually get around that? If you can't run a massive model, what is the mechanism for making edge AI actually work on this board?
You have to fundamentally alter the AI model itself to fit the hardware. Developers use a process called quantization.
Quantization, how does that work?
Instead of the model using highly precise 32-bit floating point numbers for all of its internal math, quantization compresses those numbers down to 8-bit integers.
So you're basically degrading the mathematical precision of the AI.
Yes, you trade a tiny fraction of the model's accuracy for a massive reduction in its memory footprint and computational weight.
A compromise.
A necessary one. A massive deep learning model that requires a dedicated server will absolutely choke a Pi 5. But a highly quantized, task-specific model like one, trained exclusively to recognize a specific defect on an assembly line, will run brilliantly.
So you just have to know your limits.
Understanding how to size and compress the model to fit the thermal and processing limits of the silicon is the entire art of edge AI.
Which brings us to a fascinating logistical problem. We've talked about deploying optimized headless servers running Diet Pi. We've talked about deploying Pi 5s on factory floors to run localized edge AI. Right. In all of these scenarios, the Raspberry Pi is deployed physically far away from a human, and it has no monitor or keyboard attached. How are you supposed to securely manage, update, and monitor an entire fleet of these devices?
The mechanism of remote access is the glue that holds this entire ecosystem together. You need a way to open a secure window into the machine from anywhere in the world.
And the final piece of our source material traces a really significant evolution in how this community handles that remote access.
Right.
Historically, if you had a Pi deployed in your attic monitoring your solar panels and you needed to access its desktop interface,
You got a bit of work ahead of you.
yeah, the standard operating procedure was to use a third-party software called RealVNC.
RealVNC has been the bedrock for a long time. It captures the graphical output of the Pi, encrypts it, and streams it over the network to your laptop while sending your keystrokes back.
It effectively teleports you in front of the remote machine.
Exactly. But setting it up required a non-trivial amount of network configuration.
Right. You often had to worry about port forwarding on your router, managing dynamic IP addresses, and ensuring the third-party service was properly authenticated. But here's where it gets really interesting.
The game changer.
The latest updates detailed in the blog show a fundamental shift to remove all of that friction. The ecosystem just introduced Raspberry Pi Connect.
And the shift here isn't just a new piece of software. It's where the software lives. Raspberry Pi Connect is a VNC service integrated natively into Raspberry Pi OS 12.
It is baked right into the operating system. You don't have to go hunting for third-party tools or wrestle with your router's firewall settings.
It's just there.
Yeah. As long as you are running a relatively modern Raspberry Pi 4, 400, or 5 other, you can toggle it on directly from the system menu.
The underlying mechanism of that integration is vital. By building it natively into the OS, Connect uses a secure peer-to-peer WebRTC connection.
Which
It automatically punches through complex network address translations and firewalls. From a deployment standpoint, it means an engineer can pre-configure a Pi with OS 12, mail it to a client across the country, have them plug it into any random network, and instantly have a secure, encrypted tunnel to manage the device.
Without asking the client's IT department to open network ports, that is huge.
It drastically lowers the barrier to deployment.
And honestly, looking at that shift from relying on complex third-party tools to providing a seamless, out-of-the-box native solution feels like a return to the Foundation's original philosophy.
How so?
Well, even as the hardware scales up to tackle industrial edge AI, they're still obsessed with removing the friction between the user and the technology.
It proves that powerful enterprise tools don't have to be inherently hostile to the end user. The same seamless connection that helps a corporation manage a sensor grid helps a hobbyist access their backyard weather station.
It is an incredible technological arc. To synthesize the journey we've been on today, we started by looking at a piece of hardware that intentionally strips away the sleek consumer packaging to invite curiosity.
The naked board.
Right. We've seen how that open architecture allows it to self-heal in enterprise production clusters. We explored the extreme lengths developers go to, stripping away every non-essential line of code in operating systems like DietPi to maximize constrained hardware.
Every megabyte counts.
We looked at how the massive memory bandwidth of the Pi 5 enables quantized AI models to execute locally at the edge, eliminating cloud latency. And finally, we saw how native tools like Raspberry Pi Connect make managing this entire decentralized network completely seamless.
The thread connecting all of these use cases is agency. The Raspberry Pi ecosystem is a rejection of black box technology.
You have to know what's inside.
Exactly. Whether you are deep diving into kernel optimization, compressing a neural network, or just trying to get an LED to blink using Python, the hardware demands that you understand how it works.
You can't just be a passive consumer.
Right. Knowledge is only theoretical until you apply it, and this platform is a masterclass in applied computer science.
It is the ultimate invitation to get your hands dirty. But before we wrap up this deep dive, I want to leave you with a final thought to mull over, building on what we've discussed today about edge computing.
Okay, let's hear it.
We are currently watching massive tech conglomerates pour hundreds of billions of dollars into building centralized, incredibly power-hungry AI data centers. They want everything processed in the cloud.
It's a massive arms race.
It really is. But we've just seen how a $30 naked circuit board can already handle local network infrastructure, home automation, and lightweight AI inference without ever touching the internet.
It runs offline.
So fast forward 5 or 10 years for you. As silicon continues to miniaturize and edge models become exponentially more efficient, what happens to the power dynamic of the global tech industry when you no longer need their centralized servers?
That's a profound shift.
Who truly controls the future of the internet when an enterprise-grade data center fits in the palm of your hand completely off the grid?
It is a fundamental question about the decentralization of digital power.
Something for you to think about the next time you look at a device that doesn't have a case. Until next time.